Good morning, everyone. My name is Dr. Bhavani. I am working as a DL in chemistry at TTW RDC, Karimnagar. Today, my presentation topic for online lecture competition is pericyclic reactions. So, these are the special type of organic reactions, and in these reactions, only the reactant will be converted into product without involvement of any intermediate. We can see here that the general organic chemistry reactions are involving so many steps like starting material is converted into intermediate and another intermediate and another and finally into the product. But in pericyclic reactions, the starting material is directly converted into the product through the transition state. It does not involve any intermediate. Okay, so these are the specific thing about the pericyclic reactions. These reactions are generally seen or exhibited by the double bond containing organic compounds, generally unsaturated alkene like compounds. So this is called as a concerted reactions. Without any intermediate, if the reactant is converted into product, that is called a concerted reaction, and that involves a cyclic transition state. All those things we will come across in the coming slides. Okay, so this is about the pericyclic reactions introduction. So what coming to the properties of pericyclic reactions. Okay, so that is about the introduction, and coming to the properties of pericyclic reactions, they are understood in terms of molecular orbital theory. How does these reactions occurs? All these concerted reactions, how does they occur? They are understood by some theories. That theories we will come to know one by one. So these pericyclic reactions are either initiated by light or by heat. Okay, so the reaction does not involve any solvent. That reaction does not involve any nucleophiles or electrophiles like the general organic reactions. So these require generally the light or heat, and they are completely stereospecific. They are completely stereospecific. What is a stereospecific reaction? It shows that a single stereoisomer of reactant forms single stereoisomer of product. Suppose you have cis alkene, cis butadiene and trans butadiene. Okay, if cis butadiene is giving a product A and trans butadiene is giving a product B, A and B are different, then that reaction is called stereospecific. Stereospecific means particular reactant gives only particular type of product. Okay, specific reactant gives specific product. That is called stereospecific. Stereo means the arrangement of groups, they differ in that molecule. Cis butadiene, it has two alkene groups on the same side, like, okay. Trans butadiene, they are in the opposite. So that is stereoisomers. Those two are stereoisomers. And if they give particularly one type of product, that is called as stereospecific. Okay. So properties of pericyclic reactions are, they does not involve any solvent, no nucleophiles and electrophiles are involved. They are not catalyzed by any Lewis acids like many of our organic reactions. They are highly stereospecific, and they are either initiated by light or heat. These reactions, they involve only single step reactions. They involve a cyclic stand transition state in their reactions. They either use heat or light for the reactions to occur. Okay, so how many types of pericyclic reactions are present? As of now, we are having 5 different types of pericyclic reactions: cycloaddition reactions, electrocyclic ring closing or ring opening reaction, sigmatropic rearrangement, kilotropic reactions, and group transfer reactions. But majorly in particular, according to degree syllabus, we at BSc level have only 3 types of reactions. That is the first 3 types. Okay, cycloaddition reaction, electrocyclic ring closing or ring opening, because it is a reversible reaction. It can be of both the types, and sigmatropic rearrangements. Okay, so now we are looking at the electrocyclic ring closing or ring opening reactions. So electrocyclic reaction is a pericyclic reaction. It is a type of pericyclic reaction where net result is one of the pi bond being converted into one sigma bond. See here, the reactant molecule we have taken is 1,3-butadiene, 1,3-butadiene. This is converted to cyclobutene. What had happened here? One of the pi bonds got reduced. The number of the pi bond got reduced, and one sigma bond is formed here in this product. Okay. In the same way, what is happening here? In the second one, hexatriene is converted into cyclohexadiene. Octatetraene is converted into cyclooctatriene. Tetraene is converted into triene. At the same time, this open chain structure is converted into closed chain structure. Okay, open chain structure is converted into closed chain, and this symbol which is shown here shows that this is a reversible reaction. Both the forward and the backward reactions can occur in the presence of light or heat. So this is about the electrocyclic reaction. Electrocyclic reactions converts the open chain structure to closed structure, or the closed structure to open structure. Okay. Next is cycloaddition reaction. Cycloaddition reaction is in which 2 pi bonds are lost and 2 new sigma bonds are formed, resulting in a cyclization reaction. See here, this is a alkene, substituted alkene. This is another substituted alkene. This is again a pi system. Pi system means pi bonding, unsaturated organic compound. Okay, so these compounds now, when they are mixed together, they undergo cyclization, cycloaddition. So addition, they both add together. Plus, in the electrocyclic reaction, you have only one reactant, but in the cycloaddition reaction, you will generally have 2 reactants. They get added, and these 2 pi bonds get lost, and you let it 2 sigma bonds. So 2 pi bonds are lost, 2 sigma bonds are gained. This is about the cycloaddition reaction. Cyclic structure is formed by addition of these two. So it is called cycloaddition reaction. Next is sigmatropic reaction. Sigmatropic reaction is a pericyclic reaction wherein net result is one sigma bond changed to another sigma bond. Okay. See here, this is the some alkene. Okay, the name we cannot say because R group is not specified here. This alkene contain a allyl group. This allyl hydrogen is present here now. Now this red colored hydrogen, now it is changed to the, after rearrangement, it is, or sigmatropic or movement of the sigma bond, now change it to from this place to this place. This is a sigma bond, right, between carbon and hydrogen. This sigma bond is changing its position to this place. So this is 1, 2, 3, third position, and this is 1 position. So this moment of 1 to 3 position is called 1-3 sigmatropic shift. This is 1-5. 1, 2, 3, 4, 5. So now hydrogen is moved from here to here. So this is 1-5 sigmatropic shift. Now in this triene system, that is alkene, but alkatriene, in this the hydrogen is present on 1, 2, 3, 4, 5, 6, 7. From first carbon to 7th carbon it is shifting. So this is 1-7 sigmatropic reaction. So all these 3 types of reactions, they can be undergone in a single step without involvement of any intermediate. And during these transformations, a cyclic transition state will be obtained. Okay, and this does not involve any solvents or any reagents or any acids or bases, Lewis acid, something. They involve only light or heat. So this is about the basic introduction of pericyclic reactions and its classification. Now we will study one by one the electrocyclic reactions, cycloaddition reactions and sigmatropic reactions. Okay. So electrocyclic reactions is reversible reaction. Now we have studied, just now we have read about the definitions. Again it is shown here. See here, 135 hexatriene, and in till now above the arrow nothing is shown. But if it is shown like this delta symbol, then that shows it is a heat promoted reaction. If this is shown like this is a heat promoted reaction. If it is shown like this, then it is a light promoted reaction. Okay, in that way. So this is a heat assisted reaction. So in presence of heat, 135 hexatriene gives 1,3-cyclohexadiene, and this new sigma bond is formed here. Next, cyclobutene. This is already a cyclic structure. This is converted to open chain structure, 1,3-butadiene in presence of heat. Okay, this is the heat symbol and H nu will be the light symbol. Okay, this open chain structure is converted to closed structure, and a closed structure is converted to open chain structure. So this is called as a ring closing reaction. This is called as a ring opening reaction. Okay, so in this way, the pericyclic reactions, electrocyclic reactions are of a reversible type. They can be ring closing as well as they can be ring opening reactions. Okay. Okay. So based on the number of electrons that are involved in the based on the number of electrons involved in the cyclic transition state, electrocyclic reactions are classified into 4n pi system and 4n plus 2 pi system. So n can be a integer. What is n? N means what? 4 into 1, 4 into 2, 4 into 3, like that. So in this 1,3-butadiene system, how many pi electrons we have? A pi bond will have 2 pi electrons. Always to remember, a pi bond to have 2 pi electrons. So 2 plus 2, 4 pi electron systems. So this is a 4 pi electron system. Okay. So this is called 4n pi electron system. 4 into 1 is 4. So 4 pi electron system. Whereas 135 hexatriene system is a 4n plus 2 pi electron system. Okay. So both are ring closing reactions. This is it involves 6 pi electrons. So this is called as a 6 pi electron system. So electrocyclic reactions, they can be of two types, 4n system and 4n plus 2 system. So this electrocyclic ring closure, this is the same reaction which we read in the previous slide, that can be occurred by heat or light. Heat or light, they can both help formation of cyclobutene from 1,3-butadiene. Here also light or heat can be used to convert the ring closing. Ring closing reactions can be done either by heat or light. In the same way, ring opening reactions can also be done by either presence of light or heat. Okay, so till now what we have studied, so electrocyclic reactions are two types, closing and opening, and it is of classified into 4n and 4n plus 2 systems based on the number of pi electrons involved, and these reactions are promoted either by light or heat. Okay, so in electrocyclic reactions, while the ring closing is taking place, the end carbons can undergo two types of rotations. This rotations, knowing about the rotations and their conservation is very important in giving the stereospecificity of these reactions. Okay, the end carbon atoms, okay, if they undergo rotation in same directions, then that is called as con rotation. Two types of rotations are present. Based on these rotations only, the obtaining of product is dependent. Okay, which product is obtained is dependent on the types of rotations they follow during the cyclization. Okay, so if the end carbon atoms of 1,3-butadiene, if they rotate in the same direction, then that is called as con rotation. Okay, so that is called, see here, this is rotating like this and this is also rotating like this. So this is called as con rotation. Okay, if rotation is in opposite direction at the end or termini, so then that is called anti-clockwise rotation, and that is called as disrotation. This is rotating in this direction, whereas this is rotating in this direction, opposite direction. This is called as disrotatory. Ring closure is disrotatory. But in the above thing, what happened? This is rotating right side, this is also rotating right side. So same side direction rotation is called as con rotation, whereas opposite rotation, or one is clockwise and one is anti-clockwise, opposite rotation is called as disrotation. So these rotations we have to definitely know before understanding the pericyclic reaction. So now we can see here electrocyclic ring opening. Okay, this is the, what is this? Cis 3,4 dimethyl cyclobutene. Cis means the two methyl groups are on the same side. 3,4 dimethyl cyclobutene. So if this is opened, what you will get? You will get 2,4 hexadiene you will get. So trans 2,4 hexadiene. So this can be undergone under photochemical conditions. H means photochemical condition, or thermal condition means this delta symbol shows for thermal condition. So thermal electrocyclic ring opening and photochemical electrocyclic ring opening. So this ring is opened. So if that ring is opened, now what you will get? One more pi bond and one sigma bond will be lost, right? So this ring opening can be occurred by two methods, either photochemically or thermally. In the photochemical method, you will get trans diene, whereas in this thermal method, you are going to get cis diene. This is mainly because of the rotation of this terminal methyl groups. Okay, so this is a 4N system, and this 4N system you will get, what you will get? You will get under thermal conditions con rotation, and here you will follow disrotation. So and this disrotation makes the trans diene as the major product, but cis con rotation here will give the cis trans diene as a major product. Here it is seen here, this is a 4N system, 4 pi electron system. It is, see here, this is 4 pi electrons are involved. So this is 4N system. Under thermal conditions it undergo con rotation, under photochemical conditions it undergo disrotations. Few more examples we will study here, then we will come try to understand what is this con and what is this, why it should undergo con rotation under thermal conditions, and why it should undergo disrotation under photochemical conditions. All those can be understood by understanding the molecular orbitals of these by molecular orbital theory. Okay. Next is, see here, this reaction. This is cyclobutene is converted to 1,3-butadiene, reversible reaction, electrocyclic reaction. 4N system, it undergoes, under thermal condition it undergoes con rotation, under photochemical condition it undergoes disrotation. This is 4N plus 2 system, disrotation under thermal condition, and photochemical conditions it undergo con rotation. This is again 4 pi system you have, so 8 pi electrons you have, so you will have 4N system, con rotation under thermal and disrotation under photochemical conditions. Here you have 4N, this is 2 electrons and 2 electrons from this pi bond, totally 4N. So this undergoes con rotation under thermal and disrotation under photochemical condition. So in this way, depending upon the number of the pi electrons, the type of the rotation depends under different conditions again. If it is a 4N system, it undergo con rotation under thermal condition and disrotation under photochemical condition. If it is a 4N plus 2 system, it undergo disrotation under thermal condition and photochemical condition is con rotation. So why it happens like this and all we will see. In order to understand all these, how it is overlapping, why it is overlapping, why the ring opening is taking place, why ring closing is taking place, why the rotation is specific in certain conditions, that we will understand by understanding the molecular orbital theory. So molecular orbital theory, what does it tell? So when two atomic orbitals combine, two molecular orbitals are formed. These two molecular orbitals will be designated one as the bonding molecular orbital and the other as the antibonding molecular orbital. Okay. Suppose now you have 2p and 2p orbitals. 2p means they are forming a pi bond, right? So they are, if the lobes p orbital, how will it be? It will be, p orbital will be like this. So p orbital will be like this, dumbbell shape, right? So the upper lobe will have positive sign, lower lobe will have negative sign. So if the two plus sign plus symbols they combine, what you will get? You will get a bonding orbital like this, molecular orbital. If the opposite signs they combine, you will get a anti-bonding molecular orbital like this. So this is about the molecular orbitals. So we are not bothered about the sigma bonding here. We are bothered only about the pi bonding here, because in these reactions pi electrons are involved. So pi bonding means which involves the p orbitals. P orbitals, they have a dumbbell shape and they have positive and negative sign. So they can be overlapped by the two signs, positive signs if they are overlapping, same sign if they overlap, they lead to formation of a pi bonding molecular orbital. If the opposite lobes overlap like this, they form anti-bonding pi molecular orbital. Okay. So yes, now we are going to study about the molecular orbitals. Suppose you take ethene molecule. How many pi bonds it has? It has only one pi bond. How many p orbitals are there in the ethene? Two p orbitals are there, like this. Two p orbitals they form a pi bond. So if they are like this, they are called bonding molecular orbital. If they are of the opposite side, then they will have, what is that? Anti-bonding molecular orbital. Here the number of nodes is 0, whereas in the anti-bonding molecular orbital you will have the number of nodes as 1. Number of nodes means where the possibility of finding the electron is 0. That is called as node. Okay. So when the lobes of opposite sign they interact, they form a node there. So this diagram shows about the molecular orbital, pi molecular orbitals of 1,3-butadiene. So 1,3-butadiene, what is the structure of 1,3-butadiene? It is of this type. Okay. 1, 3 butadiene. How many p orbitals it has? It has 4 p orbitals. Here, one is here, one is here, one is here, one is here, and the fourth one will be here. So all these four p orbitals are shown here and they are written in a straight manner, not in this same way. So if all the four lobes have the four plus signs on the same side, this will be a very low energy and it will have 0 nodes. So these four p orbitals, they combine to form 4 molecular orbitals. Among the 4 molecular orbitals, you will have 2 as bonding molecular orbitals and 2 as anti-bonding molecular orbitals. We know that the number of combining orbitals will be equal to the number of molecular orbitals formed. So 4p orbitals, if they combine, you will get 4 molecular orbitals. Among these, so 2 will be bonding and the upper 2 will be anti-bonding. Okay. So in the same way, if you come to the allyl radical is having this type of structure. It will have 2p orbitals in the pi bond and 1p orbital with an unpaired electron. So these 3p orbitals, if they are on the same orientation, they form the pi 1 molecular orbital. So these 3p orbitals, they combine to form 3 molecular orbitals. Okay. So first molecular orbital will be denoted as psi 1. This is psi 2. This is psi 3. Okay. In the same way, here in 1,3-butadiene also, this is psi 1, psi 2, psi 3, psi 4. So thus in the one allyl radical, you will have the psi 1 with a 0 node, psi 2 with 1 node and psi 2 with 2 nodes. So the number of nodes increase from going from bottom to the top with increasing in the energy level. So the theory is explaining pericyclic reactions. Pericyclic reactions are better explained by 3 different scientist groups over a period of time. And these the main theories which are accepted mostly are first developed by William and Hoffman. They are called as conservation of orbital symmetry. And second one is FMO, or called as frontier orbital theory. It is also called as frontier orbital theory or frontier molecular orbital theory. First is developed by Woodward and Hoffman. So that is conservation of orbital symmetry and aromatic transition state theory. So all the three, they can interpret about the pericyclic reactions correctly. But in order to understand in an easy manner and to get a clear idea, we are following today in our lecture about the frontier molecular orbital theory. So how does this theory explain the formation of the products stereospecifically? Okay. So the molecular orbitals of a pi system, some rules we have to know before going into detailed study. Okay. So according to linear combination of atomic orbitals, mixing of atomic orbitals produce molecular orbitals. This we know. Number of p orbitals combined will be equal to the number of pi molecular orbitals produced. This also we know. Each p orbitals has two lobes with opposite phases of wave function of the two lobes, plus and minus indicated waves. So each p orbitals has two lobes. One lobe will be plus and one lobe will be minus. So number of p orbitals combined will be equal to number of molecular orbitals produced. And we can know that antibonding molecular orbital energy is more than bonding molecular orbital. And sometimes we also have non-bonding molecular orbital also. So that will be in a medium of energy. Okay. So now we are going to look into the orbital diagrams of ethene molecule, or ethylene also you can say it as. Ethylene is a combination of two p orbitals. The pi bond is a combination of two p orbitals. If they are in phase, possible arrangement of p orbitals, how can they arrange? In phase, because the same lobes are on the same side. The same sign lobes are on the same side. This is in phase. This is molecular orbital is called as bonding molecular orbital, and it is denoted by psi1. This is called psi1. If they are out of phase, means the same lobes are on the opposite side, then there will be a node here. Node is there is no chance of finding electron here. So this molecular orbital will have a node, and it is denoted by the psi2, and this is called antibonding molecular orbital. Okay, so under normal conditions, the two electrons of the ethene molecule or ethylene molecule, they are present in the psi1. They are present in the psi1 molecular orbital. The two electrons are present like this in the psi1 molecular orbital. Suppose if some light is falling on this, and you have a very high intense light that is falling on this molecule, then you need to that one of the electron from the molecular orbital jumps into the antibonding molecular orbital. So one of the electron from the psi1 jumps into the psi2 by absorption of light. Okay. So now in the ground state, the electrons are present in the psi1. This is called highest occupied molecular orbital. Now in the normal conditions, under thermal conditions, the two electrons are present in the psi1. That is called as highest occupied molecular orbital, or HOMO. And psi2 is not with having any electrons in it. So that is called lowest unoccupied molecular orbital. Okay, that is called as lowest unoccupied molecular orbital. Next, we are going to deal with the 1,3-butadiene molecule. 1,3-butadiene molecule, how many pi bonds it has? 4 pi bonds. How many p orbitals it has? 4 p orbitals. So 2 pi bonds and 4 p orbitals. So the 4 p orbitals combine to form 4 molecular orbitals. So the 4 p orbitals combine to form 4 molecular orbitals. So those among the 4 molecular orbitals, the first two, psi1 and psi2, are called as, what are they? Bonding molecular orbitals. But psi3 and psi4, they are called as antibonding molecular orbital. In the ground state or in the thermal conditions, the 4 electrons of the 1,3-butadiene are arranged in the psi1 and psi2 energy levels like this. Okay. Okay, so now this Psi2 with two electrons is called as highest occupied molecular orbital. Okay, and in the ground state, Psi3 with no electrons is called as lowest unoccupied molecular orbital. Okay, and now if this 1,3-butadiene system is irradiated with some light, what happens? One of the electron jumps from the Psi2 to Psi3 molecular orbital. Okay, now in the excited state or in the photochemical conditions under photons, what is the now highest occupied molecular orbital? Psi3. And what is the lowest unoccupied molecular orbital? Psi4. Okay, so under ground state or under thermal conditions, the HOMO and LUMO are different, and under photochemical conditions, the HOMO and LUMO are different for any given molecular system. Okay, so now we are going to study about the 135 hexatriene. Okay, this is the system, and it has 3 pi bonds. So 6 p orbitals are involved in it, and 6 p orbitals combine to form 6 molecular orbitals. The 6 molecular orbitals are denoted by psi1, psi2, psi3, psi4, psi5, psi6. Among these, the first 3 are bonding molecular orbitals and the later 3 are anti-bonding molecular orbitals. In the ground state, all the 6 electrons are filled in the first 3 bonding molecular orbitals. Now the HOMO here is the psi3. Highest molecular occupied molecular orbital is psi3 and LUMO will be psi4. Under photochemical conditions, light will fall. If light falls on this molecule, it will get energized and one of the electron jumps into the psi4. So now the HOMO becomes the psi4 and LUMO becomes the psi5. So in this way, molecules behave differently under thermal and photochemical conditions. Under thermal conditions, they behave normally. Under photochemical conditions, they get energy and they jump into the one of the electron jumps into the higher energy level, so that the energy level changes their names. The HOMO and LUMO changes. Okay, so now we can see here, this is the hexatriene system. The top two are psi3. Okay, psi3. You know, psi3 of this molecular orbital, the ending carbon atom p orbitals you have to check. What is the same sign with on the same side? Okay, here also same sign on the same side. So now this HOMO under thermal condition, if it undergo disrotation. Disrotation means this orbital will be rotating like this orbital will be rotating like this, clockwise, anti-clockwise, this leading to formation of bonding. So 4n plus 2 system under thermal condition, it undergo disrotation to form the product. And 4n plus 2 system under thermal condition, if it undergo con rotation, there is no bonding formed. Okay, no bond is formed, anti-bonding. It is not allowed, it is called forbidden. Okay, now the psi4 system under photochemical condition. This psi4, how you get the psi4? Under photochemical conditions, psi4 becomes the under chemical conditions, psi4 becomes the HOMO. Okay, so this psi4, if it undergoes con rotation, it is called bonding is allowed. Con means same side rotation. If it is undergoing this rotation, anti-bonding forbidden. So conclusions that can be drawn from here is 4n plus 2 system. What is that? Ground state is disrotation. Okay, 4n plus 2 system, under thermal conditions, disrotation is allowed. Under photochemical conditions, con rotation is allowed. Whereas 4n system, we have just earlier studied, under thermal conditions, con rotation is allowed. Under photochemical conditions, disrotation is allowed. So in this way, the molecular orbitals and their interactions, they are the main role playing in deciding the stereochemistry of the product that is obtained. So this is 4n system. Okay, 1,3-butadiene system, you have 4 p orbitals in the molecular orbital, and this under photochemical conditions, this psi3, it becomes the HOMO. This, if it undergoes con rotation, anti-bonding interaction not possible. If it is a disrotation, then only it is a bonding interaction. Okay, so you have to know that the electrocyclic reactions are stereospecific, we are saying. See here, cis and trans 3,4-dimethyl cyclobutene are stereoisomers. See here, these two methyl groups are on the same side. This is called cis. And these two methyl groups are on the opposite side. One is wedge. Wedge means front side. One is broken. Broken means back side. So these two are called trans. Okay. So these two are stereoisomers. One is cis, one is trans. They differ in their stereo positions. So this is called stereoisomers. If they are opened, electrocyclic ring opening, if it occurs, they give two different products, cis trans and trans trans, under thermal conditions, because they are stereo specific. The ring opening occurs by con rotation here under thermal condition, because it is a 4n system. Okay, if it is a 6 pi electron system, then the photochemical conditions undergo con rotation, whereas thermal conditions undergo disrotation. Okay, see here, these two are like this. One is like this, one is on the other side. If it is a disrotation, disrotation means this methyl group moves clockwise, this methyl group moves anti-clockwise, so they come on the same side. So this rotation is allowed for what is that, thermal conditions, whereas in order to form a bond, whereas for photochemical conditions con rotation is allowed. Okay. Okay, so this Psi3 system, again it is shown clearly. So what is disrotation and all, the end, the p orbital which are present at the ends are here. If they are moved like disrotation, one is like this, one is like this, then only it will form a bond in between these two. Okay, so 135 hexatriene under thermal condition, it undergo disrotation, so that the two R groups present on the terminal carbons, they come together and form a cis molecule. Okay, electrocyclic reactions are stereospecific. Again the same thing, electrocyclic ring closure it is shown here. Previously electrocyclic ring opening was shown. Okay, the orbitals of terminal atoms of HOMO rotate by 90 degrees, and the rotation occurs in same direction, that is called con rotation. If it occurs in opposite direction, that is called a cis rotation. So this another example you can see here. See here, this is a trans compound with a cyclobutene. Okay, so this is a trans, one methyl group is above and one is below. So under as the carbon rotates, the substituent rotate with it. Okay, so now if that carbon is rotated in order to form an open chain structure like this. Okay, so this becomes a foreign system under thermal conditions. It should undergo the con rotation. Con rotation means same side it should rotate. Now if this rotate like this and if this rotate like this, what will happen? This will come to the bottom and this will go to the top. So this will form the trans compound. This will give us the product like this. Okay. So in the same way, you also see here the con rotation is clearly seen here under photochemical conditions. The 135 hexatriene system, it undergo con rotation. Then only it can form the bonding like this. Under thermal condition, it should undergo disrotation, because under thermal condition, the Psi3 system is used. Under photochemical conditions, the HOMO will be Psi4. So there is a change. Okay. So next is cycloaddition reaction. Cycloaddition is a pericyclic chemical. So now we have come to a conclusion for electrocyclic reactions. So electrocyclic reactions are those which can be occurred either photochemically or thermally, and electrocyclic reactions are two types. They are, one is foreign system and one is foreign plus 2 system. So foreign system behave differently, and foreign plus 2 system behave differently under thermal and photochemical conditions. Under thermal conditions, foreign plus 2 system undergo disrotation, whereas under photochemical condition it undergoes opposite rotation like that. So we have seen why they undergo, because the under thermal condition one molecular orbital will behave as a HOMO. Under photochemical condition a different molecular orbital will be behaving as a HOMO. So if the HOMO is psi 3, then that lobes will be the lobes of the terminal carbons will be having the signs, maybe a positive same signs on the same side or on the opposite side. So depending on that lobes only the rotation should take place to form a bond. Okay, so today now we are going to discuss about the cycloaddition reaction. Cycloaddition is a pericyclic reaction wherein you combine two moieties A and B, the unsaturation systems, and you lead to the formation of a new structure wherein you will have two new sigma bonds. All two pi bonds will be lost. Okay, so this is a best example for this cycloaddition reaction is a Diels-Alder reaction, very well known example in organic chemistry. So this can be 2,2 cycloaddition or a 2,4 cycloaddition. Cycloadditions can be of 4n system as well as 4n plus 2 system. So Diels-Alder reaction is the best example here. This is the 1,3-butadiene is the a diene, and the dienophile is a ethene. So these two when combined they give the cyclohexene. This is the best example of Diels-Alder reaction. This is called Diels-Alder reaction. When 1,3-butadiene combines with ethene, this gives the cyclohexene. This 1,3-butadiene is called a diene, whereas ethene is called the dienophile. So these two combine to form the cyclohexene. This is the cycloaddition reaction. This is a two unsaturated compounds are combining to give the cyclic structure. This is called cycloaddition reaction. So the cycloaddition reactions are of two types. One is 4n system and 4n plus 2 system also. Here also we have the same thing. 4n system means, see here, you have two ethene molecules. They combine to give cyclobutane. How many pi electrons are involved here? 4 pi electrons. So this is called 4n pi electron system. Whereas Diels-Alder reaction giving rise to cyclohexane involves 6 pi electrons. So this is 4n plus 2 pi electron system. Okay, so in the electrocyclic reactions we have discussed about the rotations, on rotation, dis rotation. Only rotations should give the same orbitals to overlap and resulting in the formation of the sigma bond, right? But here we have to discuss about to another concept, that is suprafacial and antarafacial overlap. Okay, suprafacial overlap and antarafacial overlap. See, yes, migration within the same phase is called as suprafacial and migration with opposite phases is called antarafacial. Suppose you have a ethene molecule and this is another ethene molecule. Now they have to come together to combine and form a cyclobutane, right? So if they come together with the same lobes on the same side interacting like this, green and green, this is called suprafacial. Whereas here in this you can see that these two are lobes are matching, but these two are not matching like this. These two are matching like this. Okay, this is called antarafacial. So this matters in cycloaddition reactions. Okay, so now we are going to discuss about the Diels-Alder reaction. So Diels-Alder reaction, you have a diene and one is dienophile. Diene is the 1,3-butadiene and dienophile is the ethene. So always cycloaddition reactions, there is a rule according to frontier molecular orbital approach. There is a rule saying that if HOMO and LUMO, HOMO of one and LUMO of one should have overlapping, that is suprafacial overlapping, then only a cyclo product will be formed. Okay, A and B you have two different things. Okay, you should take the HOMO of one molecule and LUMO of one molecule and try to combine by their suprafacial overlap. If they overlap, then that molecule will be formed like that. Okay. So now you see here, this is the diene, 1,3-butadiene HOMO. What is HOMO? Highest molecule, occupied molecular orbital of 1,3-butadiene. How it is a psi 2. How does that look like? See, remember the lobes here, opposite side lobes. Opposite side lobes are presented. They just see here. We will get the same. We'll go back to that and see here. So HOMO of 1,3-butadiene is, what is that? At the edge carbons you will have opposite lobes, right? So here the same thing we have. So this is about the 1,3-butadiene HOMO. And LUMO of diene we know, lowest unoccupied molecular orbital of ethene. Ethene, it has only two, psi1 and psi2. Always psi2 is the LUMO. Okay, the orbitals are like this. We know that. Now, if this HOMO and LUMO of diene and dienophile, if they have suprafacial overlap like this, suprafacial, then you will get a formation of a cyclohexene. Okay, the product is formed. And here you can see, now you have taken the HOMO of diene and LUMO of dienophile. In this next case, you can take the LUMO of diene and HOMO of dienophile. HOMO of dienophile means ethene, we know this is the HOMO, psi1. Okay, LUMO of, what is that? Diene. It will have same lobes on the same side because this becomes psi3. Okay, so these two overlap suprafacially, same lobes on the same side, so suprafacial overlap, and it results in the formation of the cyclohexane product. So now you can see here, during the formation of cyclobutane, when two ethene molecules are involved, one ethene molecule in the HOMO, another ethene molecule in the LUMO, under thermal conditions, they are not allowed because this is not supra overlap. See, these lobes are not of the same, say lobes are not on the same side. This is not allowed under thermal conditions. It is not allowed. Under photochemical conditions, what happened? The HOMO, one of the electron from this ethene molecule enter into the second psi2 molecular orbital. That becomes HOMO now. So this is the HOMO and this is the LUMO, and these two overlap, and this reaction is possible under photochemical conditions. Okay, so this cycloaddition reactions, you have to follow the supra overlap only, then only the bond is formed. If that is supra and antara like this is supra. This is not possible to overlap here. So this will overlap with that lobe which is present above. This is called antarafacial overlap. So antarafacial overlap, bond formation is not possible. Okay. So you can see here the 1,3-butadiene and a substituted alkene. If they are combined together, what is the product you are going to obtain? This is the product. So this X and Y are on the same side. In the product also they are on the same side. You get the cis product only. Whereas you take the same 1,3-butadiene here, but you take the ethene, the substituted ethene with the two substituents on the opposite side, then this is called trans, and the obtained product is also trans. In this way, we can say that pericyclic reactions are very, very stereospecific. Cis gives cis product, trans gives trans product. This will not give this product, and this will not give this product. So this is very stereospecific reactions. So this cycloaddition reaction, Diels-Alder reaction. Again, you have a 1,3-butadiene and a vinyl nitrile. This is called vinyl nitrile. You get cyclohexene. So this is about and again you are taking this as a diene and dienophile. If you take, the big product will be obtained as the final product. Okay, so this is the diene here, and this is the more examples I am giving in case of a Diels-Alder reaction, very much useful for PG entrances. So this is diene and this is the dienophile, they combine to give this cyclic adduct. Okay, here this is the diene and this is the diene and this is the dienophile. So this structure is changed, that's it. This structure is little envelope structure is there, no? This one, there adds cyclopentene, pentadiene. So it has taken the envelope structure, and alkene, the pi bond is shifted here, and one of the pi bonds from this system is used in formation of this adduct. Okay, so this is about the cycloaddition reaction. So cycloaddition reactions, it is of two types, 4n and 4n plus 2 system. Best example for 4n is cyclobutane formation from two ethene molecule, and best example for a 4n plus 2 system is the Diels-Alder reaction. So what is the condition for cycloaddition reactions? So the suprafacial and arrangement, if the molecular orbitals have, they overlap and form the bonds. Cycloaddition takes place readily. If the supra-antarafacial, then that is not occurring. Okay. Next one is the Sigmatropic rearrangements. It is a type of molecular rearrangements wherein sigma bonded atom or a group which is in combination with the pi electron shift systems, the sigma bond now will be moved to a new position and the pi bonds are also reorganized. So this total process is called sigmatropic reactions. The total number of sigma bonds and pi bonds remains same. So different types of sigmatropic rearrangements we have, like 3 comma 3 sigmatropic rearrangement, 1 comma 5, 1 comma 7, 1 comma 3, 2 comma 3. So many types of non-organic reactions like Claisen rearrangement, Cope rearrangement, all these involves the sigmatropic reactions. I am not dealing with organic reactions here. I'm just letting you know or letting clear about what is the sigmatropic reactions, how many types of sigmatropic rearrangements are there. It is a unimolecular reaction, right? Electrocyclic reactions, this is also a unimolecular reaction. But whereas cycloaddition reaction is a bimolecular reactions, you need to have two molecules for the reaction to take place, cycloaddition reactions. But in sigmatropic reactions, only one molecule is enough. See here, this is called a allyl, sorry. Okay, this is a allyl. Okay, allyl, and you have a R group here. So if you see here, this R group is changing its position from here to here, and this pi bond is moving from here to here. This movement of sigma bond from one place to another place, and this sigma bond is in combination with the pi electron system, is called as sigmatropic rearrangement or sigmatropic reactions. A reaction in which sigma bond migrates from one end to another of a pi electron system is called a sigmatropic reaction. Migration of sigma bond takes place with atom or group from a allylic alpha position of unsaturation to new. This is called a allylic position. Okay, from this position to new position across the pi system, the sigma bond is moving. So this is called as sigmatropic reaction. Okay, so the way migrating group, where is that place is called as this place. Suppose see here, this is a pi bond, then which is alpha carbon to it, this is alpha carbon. This alpha carbon, one of the group from here will now migrate to this place. Okay, so this place is called migrating origin and this is called as migrating terminus. Okay, the bond is broken here, the bond is formed here, this is called migrating origin, this is migrating terminus. Okay, moment of sigma and pi bond occur in opposite direction. If that sigma bond is moving in this direction, pi bond will be moving in this direction. Okay, so this is called a 1,3 sigmatropic shift because see here, this is a 1, 2, 3, 3 carbons. Okay, and this is 1. Okay, so this 1 and this 3, the first place to third place it is moving, so it is called 1,3 sigmatropic rearrangement. In the next thing you can see here, this is 1, 2, 3, 4, 5. Now this hydrogen is moving from this place to the final carbon, fifth carbon. So this is called as 1,5 sigmatropic rearrangement. What is happening here, as the hydrogen is moving to the right direction, the pi bonds are moving to the left direction. These two pi bonds are moved now. This is moved here. So this is called 1,5 sigmatropic rearrangement. So Woodward, he has given the nomenclature for studying or for designating the molecular rearrangements. Okay, sigmatropic rearrangements. So he has said, see here, this is a J, means the carbon atom, the carbon skeleton which is stable. He has this molecule, this is not moving, no, this only hydrogen is there which is moving. So this is named as I is equal to 1. It is called as J is equal to 1, 2, 3, 4, 5, 6, 7 we have. So this I is 1, this is moved from this place to this place. So this is called 1,3 sigmatropic shift. Okay. The next thing, what is there? This hydrogen is moved from 1 to 5th position. Okay. I is 1, J you have 7. But from 1 to 5th it is moving, and so it is called as 1,5 sigmatropic shift. In this case, it is clear. It is a it is significant. You can see here that this carbon atom, which is attached to the first one, this is moving, and this one, not only one, but the third place is also moving. Okay, this is moving. This is moving to 1, 2, 3. This bond, this carbon is bonded to the new place. At the same time, 1, 2, 3. This carbon is involved in the new sigma bond formation. Now this is called 3, 3 sigmatropic shift. In the earlier cases, you can see that this is just removed from here and attached on the third carbon. So this is called 1, 3. This is removed here and attached on the fifth carbon. So this is called 1, 5. But here it is not thus like, not in the same like in the above cases. Here this is removed, but it is not the same which is attached here. It is this carbon, the third carbon is attached here, and the electrons are moved here. So this one is called as 3, 3 sigmatropic rearrangement. So in this way, the sigmatropic shifts are of different types. Sigmatropic migration of a group in supra and anterofacial pattern. See here, this is a carbon chain. You have the ending lobes like this, and in that carbon, and this carbon, you have a hydrogen here. This hydrogen is moving from the same lobe to the same type of lobe. If it is moving like this, this is called a suprafacial rearrangement. If the two lobes are and the ending carbons are on the opposite side, this hydrogen is moving from here to here. So this is migrating origin, migrating terminus. This is antarafacial rearrangement. Okay. So see here, this carbon atoms chain, this is whole chain, and the ending carbon p lobes are like this. These both are in opposite. So this is what is having this carbon, whatever, suppose if the carbon is migrating along with that hydrogens, this carbon is having a p orbital. These lobes are oriented like this is called supra, and if it has to interconnect like this is called antarafacial rearrangement. You can see here, this is allyl. Okay, allyl group. This allyl group has C double bond C and CH2, CH3 here. Okay, so this carbon hydrogen now has to shift from 1 to 3. It has to move from first carbon to third carbon. Okay, so if that carbon atom here and here, they both have the same lobes on the same side, that is called suprafacial, or if they are like this opposite, then that is called antarafacial. This is not possible. If it is suprafacial, then only the sigma group, sigma bond migrates easily. If it is not like that, it will become very difficult for the sigma bond to migrate from one place to another place. So see here, this is the allyl group with a hydrogen. So if the light falls on this, what happens? This involves the 1, 3 photochemical shift. So this photochemical condition, this is a allyl radical. It will have what is that? Homo as the excited state of alkene. So this will be of the same kind of lobes if they are present. Then this hydrogen can be easily shifted. Electrons are allowed suprafacially. It can happen. Suppose if this is not like this, if the hydrogen has to shift from a lobe of a opposite sign to a lobe of a different sign, then this is called antarafacial. Okay, so under thermal conditions, this is the molecular orbital of this system. In this molecular orbital, the end carbon atom p orbitals have the opposite lobes, so that this hydrogen cannot move suprafacially here. So thermal 1, 3 shift treated as what is that? Antarafacial shift of hydrogen from first carbon to the third carbon. So antiartificial is not that encouraged. Okay. So here we can see here that sigmatropic shift of hydrogen which is present on the first carbon 1, 2, 3, 4, 5. From this place it is moved to the fifth carbon place. So this is called a 1, 5 shift, and in the 1, 5 shift you can take it as 4n plus 2 system. This 4n plus 2 system will have the psi 3 molecular orbital. In the psi 3 molecular orbital, We can remember that the ending carbon atom p orbitals are of the same type, so this occurs suprafacially. Okay, now this, see here, this example, you have the hydrogen shift from 1 2 3 4 5 6 7th carbon. So first carbon to 7th carbon the hydrogen is shifted, so this is called as 1-7 shift. So under thermal conditions, this has so foreign system, so it is antarafacial. Okay, foreign plus 2 system, it is suprafacial under thermal conditions. Under thermal condition, if it is foreign system, it is antarafacial. So in this way, the pericyclic reactions are better understood by molecular orbital diagrams. If we can understand and write the molecular orbital diagrams for each and every system and know what is thermal and what is photochemical condition, so we can easily understand the pericyclic reactions. So coming to the summary of what we have studied, so these are the reactions which can form variety of carbon-carbon sigma bonds. We can see here that 1-3 shift, 1-5 shift, like that carbon atom sigma bonds are moving. In case of cycloaddition reactions also, we have combined two different moieties with very ease. In organic chemistry, it is not that easy to form a carbon-carbon sigma bond. It requires lots of reagents and conditions. But in under pericyclic chapters, we can see that many of the carbon-carbon reactions are sigma bond formations occurs very easily here. So less possibility of generation of unwanted side products. These are all the advantages of pericyclic reactions when compared to normal organic reactions. Less possibility of generation of unwanted side products. Here the side products possibility is very very less, because the reactions are very specific. If they occur 100%. If they don't occur, they don't undergo any reaction. So this is very stereo specific. Enormous applications it finds in biosynthesis. Pericyclic reactions, they find very large applications in biosynthesis. So today we have studied about the pericyclic reactions. They are of three types: electrocyclic, cycloaddition, and sigmatropic reactions. And again, all these three are of two types: foreign system and foreign plus 2 type. So this foreign plus 2 and foreign, they behave differently under thermal and photochemical conditions. And for electrocyclic reactions, you have to see that the con and dis rotations are followed correctly, so that the compounds which we expect are formed in cycloaddition reactions. They undergo suprafacial and anterafacial additions. In the same way, sigmatropic shifts also follow the suprafacial and anterafacial orientation of the groups for the product to be obtained under specific condition, either thermal or photochemical. Okay, so this is about the what discussion on pericyclic reactions, their types, and more examples can be studied by the interested people. On this, there are many books, Shutoshkar and all, you can read. You can have a great idea on the pericyclic reactions. More examples can be found. Okay, and I would like to thank the head office for giving me this opportunity of to participate in the online lecture competition. Thank you, one and all.